Next we will discuss about energy band diagrams for semiconductors. First of all, we will see for intrinsic semiconductor, what is the energy band diagram? We know that in a intrinsic semiconductor, N is equal to P is equal to Ni. That is, number of electrons and holes are always equal in number and equal to Ni, which is intrinsic concentration. In energy band diagram, the probability that the energy level occupied by an electron is given by Fermi-Dirac probability function. Which is Fe is equal to 1 by 1 plus e power e minus ef by kT. This is Fermi probability function. This is a probability function that the energy level is occupied by an electron, where K is Boltzmann constant in electron volt per degree Kelvin, T is equal to temperature in degree Kelvin, Ef is equal to Fermi level in electron volt equal to energy level occupied by an electron in electron volt. Here basically this Fermi level is a characteristic energy for the crystal. That is, the Fermi level EF indicates the probability of occupancy of an energy level by an electron. In intrinsic semiconductor, the probability of finding an electron in the conduction band is 0, and the probability of finding a hole in the valence band is 0 at absolute 0, that is T is equal to 0 degree Kelvin. We know that at T is equal to 0 degree Kelvin, absolute 0, intrinsic semiconductor acts as an insulator. There is no conduction. Therefore, there is no electron in the conduction band. If there is no electron in the conduction band, means there is no hole in the valence band. So, at T is equal to 0 degree Kelvin, no holes in conduction band, no holes in valence band, no electrons in conduction band. That is, if you draw the energy diagram, this is energy. This is a valence band. Conduction band. This is forbidden gap. So this is EC, this is EV. Here EC is the lowest energy level in conduction band. EV is highest energy level in valence band. So this is the highest energy level in the valence band. This is lowest energy level of conduction band. So as the temperature increases, then what happens? Number of electrons and holes gets generated, and they are equal in number. So as temperature increases, equal number of electrons and holes get generated. Hence, probability of finding electron in the conduction band and probability of finding hole in valence band is same, because number of holes and electrons are generated in same number. Therefore, probability of finding electron in conduction band is equal to probability of finding hole in valence band. Therefore, Fermi level is equal to EC plus EV by 2. So in this particular case, Fermi level is given by EC plus EV by 2. So in the energy band diagram, the Fermi level for the intrinsic semiconductor lies in the center of the, exactly center of, this is Fermi level EF. Exactly, it lies in the center of the forbidden energy band or forbidden energy gap. So hence the energy band diagram for intrinsic semiconductor is like this. Here the Fermi level at center of the band indicates equal concentration of electrons and holes. N is equal to P. This particular line indicates N is equal to P. So this is the energy band diagram of intrinsic semiconductor. Now we will say energy band diagram for extrinsic semiconductor. So when the impurities are added to intrinsic semiconductor, it will become extrinsic semiconductor. So we are having two types, N type and P type. So N type is donor impurity, P type is acceptor impurity. Here majority carriers are electrons. Here majority carriers are holes. Now we will see how the energy band diagram looks for a n-type first. So this is energy. This is conduction band. This is valence band. This is forbidden band. Now this is similar up to valence band. Up to this same as intrinsic semiconductor. But the difference here is impurity is added. So that impurity arises another energy level. This is in general EC, EV. So the impurity what we are adding, donor, arises another level which is very close to conduction band. Because of this donor impurity we will have more free electrons. That's why it is close to EC. This is called ED, donor energy level. So the distance between this ED and EC is very less. So here more donor impurities are there. So because of lesser distance, even at room temperature, almost all extra electrons, because in donor we have some extra electrons, so all extra electrons will jump to conduction band. That is, they are available for conduction even at room temperature. Hence number of free electrons is very large in case of n-type material. So due to this more number of free electrons, the probability of occupying the energy level by the electrons towards the conduction band is more comparing to valence band. So the probability of what is Fermi level? Fermi level is nothing but probability of occupying an energy level by an electron. So because of more number of electrons, even at room temperature, they will try to jump to conduction band. Therefore, due to more number of free electrons, the probability of occupying the energy level by the electrons towards the conduction band is more. So the probability level is not at the center, it is very close to or close to conduction band, but less than ED. So the Fermi level is like this. So in n-type material, the Fermi level shifted towards conduction band, but it is below the donor energy level. So this is the overall energy band diagram for a n-type material. Similarly, if you see p-type, so in p-type also the energy band diagram looks like this. Energy, this is a conduction band, this is valence band. So here we are adding acceptor impurity. This is EC, this is EV. We are adding acceptor impurity. So acceptor impurity means more number of holes. So due to this, large number of holes get created in the valence band. Holes are always in valence band. So the acceptor energy level corresponding to acceptor impurity is close to EV, EA. So this is acceptor impurity energy level because of impurity, p-type impurity. Just above EV. So even at room temperature, the electrons from valence band jump to acceptor energy level, because here more number of holes are there, more number of holes. Valence band will have initially electrons. So even at room temperature, the electrons will jump and occupies the holes in the acceptor energy level. So by default, more number of holes created in valence band even at room temperature. More number of holes created in valence band. So this shifts the Fermi energy level towards the valence band. So the Fermi level is towards valence band. This is EF. Because the probability of occupying an energy level is high at EA. So that's why the Fermi level shift towards valence band. So the overall energy band diagram is this. So here Fermi level shifted towards valence band but above A. Next we will see effect of heat or temperature on semiconductor. So at absolute zero, semiconductor acts as an insulator. That is no conduction. We know this. So when it is heated, heating means the temperature rising. So when it is heated, the temperature increases. So due to thermal energy, the electrons which are involved in covalent bonds break away from their atoms. So covalent bond will break when temperature increases. So temperature increases means covalent bond breaks. That is implies nothing but free electrons. Generates free electrons. So these electrons move from valence band to conduction band. So these free electrons constitutes current. So when a free electron is generated, a hole is also generated in valence band, which also helps for the conduction. Suppose I am increasing the temperature. The temperature increases, more thermal energy gets generated, so more electron hole pairs get generated. Hence, large number of free electrons are available for conduction. So the semiconductor behaves like a good conductor at high temperature. The semiconductor behaves like a good conductor at high temperature. So the characteristic is something like this. This is temperature T, degree Kelvin or degree centigrade. This is current I. So this is 0 degree Kelvin, absolute temperature, 0 current. So as the temperature is rising, current also rising, which is a exponential characteristics. That is, as temperature increases, conductivity increases. That is, I in current is increasing. That is conductivity increasing. Conductivity of the semiconductor increases. So conductivity increasing means what? resistance of the semiconductor decreases. So as the temperature increases, resistance decreases. Therefore, semiconductor is said to have negative temperature coefficient. Negative temperature coefficient. So this is the effect of temperature on a semiconductor. Similarly, the effect of light on a semiconductor. So effect of light on a semiconductor is also same effect of temperature. Here light energy causes electrons to break their covalent bonds. So under the influence of light energy, electron hole pairs get generated in a semiconductor, increases its conductivity. There heat energy, here electron energy. So effect of light on a semiconductor is same as effect of temperature.